Okay, let's move into the worksheet number 11 from lecture number 11. In this lecture, we mainly talk about the pressure and the pressure principles, right? So pressure, as we discussed, can be defined it as force per unit area, and unit is newtons over meters squared, right? So that units we call it as Pascal, right? That's the standard unit of the pressure. So now we discuss how pressure change because of different cross-sectional areas, and by applying the same force by different cross-sectional areas, how pressure going to be changed. In addition to that, we discuss about very important principles in here. One is the Pascal principle. Right, so Pascal principle also pressure equal F over A. In one way we can say it's a Pascal principle, and in addition to that, Pascal principle is saying to measure the pressure of depth or height by using the principle that we can write. If I have pressure P naught in this place, if I need to find the pressure at this point, that will be equal to pressure at P naught plus the media density that have, and G, and this depth is H, right? That is called it as the Pascal principle. If you need to calculate the pressure above the P naught, only difference is your pressure going to be lower. That means the second part I have rho G H will be a negative number when you go to the above the P naught. Okay, so P naught we usually use the atmospheric pressure. So now later on we discuss about the Archimedes principle. Okay, so Archimedes principle is a way that you can talk about the buoyant force, right? Or else buoyant force. So or else that we call it as the water displacement rule. What that means is, if you have a beaker fill up with some liquid, we'll say water in here. Now, I plan to drop some object in here. What will happen is, if I keep the beaker here and when I drop this object, everybody know what will happen is some of the water will display. Now, if you take the mass of this fluid times G, that is, we call it as the buoyant force that act on this object. That force is in upward direction. That's how we can calculate that force, right? So that's where that you can describe the apparent weight and those things by using the buoyant force, because it's not the real weight. When you have object inside the fluid, you will feel the object has less weight. So that's because of there is buoyant force acting on the upward direction that will make the weight little less than the your real weight. That is called it as apparent weight. Okay, so now lastly, we talk about Bernoulli principle. Right, so Bernoulli's principles also very important. We are talking about the laminar flow in this case, right? Not like turbulence flow, but Bernoulli principle explain very important things that it explain, like call it as flow rate Q, and then that will be able to write the cross-sectional area of the liquid tube times the velocity that liquid coming out on that cross-sectional area. And this will explain that this is a constant if it is a steady flow, right? Then what it says is, if you have cross-sectional area greater, then velocity should be lower. What that means is narrower tube has greater velocity and wider tube has small velocity. So that is part of the Bernoulli principle. But that is not actually directly the Bernoulli principle. And then Bernoulli principle explains that how velocity and the pressure will change. When the velocity is increasing, pressure is decreasing if it is in the same height, or you can say it's a steady flow, it's the same height. But by information about the Bernoulli principle, keep it everything into together in the formula form, that will be able to write it as V squared plus rho g h equal constant. What that means is, you can see from this formula, this is pressure and this is density of the fluid that will travel. This is velocity, this is density g, and the height. What it says is, if you have a tube like this, right, we'll say I have something like this. Right now, everybody know that cross-sectional area here, we say A1 cross-sectional area here is A2. So A1 is less than A2, right? So now this also saying that about the velocity, how the velocity will change, V1 is greater than V2, right? So now that is your flow rate condition, right? So now after that, how you check the velocity with the pressure is by using this formula. You can see here, when the velocity is greater, you will see, we'll say they have the same height, then pressure should be lower. What that means is, in this case, you can say pressure of 1 is lower than pressure at point 2. Point 1 and 2 is labeled in here, right? That is the conceptual understanding of the Bernoulli principle. Okay, that will be mainly what we discuss in this lecture. So let's move into the first question and go step by step. Okay, so I'm going to make the space in between also when I do the problem. Then we have space to write, right? Okay, so now let's see first one, right? So when you stand on one foot instead of two, explain what will happen to the force and pressure you exert on the floor. So I just want you to understand the definition of the pressure and separate what is the force, what is the pressure. That's the idea about here, right? So you stand on one foot. Okay, so you stand on one foot or 2 feet. What is the same in this case? You stand in 1 foot or you stand in by using your 2 feet. So what is the difference between these two? Right? You basically changing your cross-sectional area onto the floor. That means your body weight is distributed to 2 feet instead one when you are sitting on 2 feet, right? So now you stand on 1 foot or 2 feet. It does not change the force of gravity. Force of gravity is your body weight. It is still the same. Is the same, right? But pressure, but cross-sectional area is different, right? So because of that, we know that pressure equal force per unit area. So now this is force of gravity. When you sit on 2 feet, you basically increase in the cross-sectional area. That means what you are doing is decrease in the pressure. Okay. So that means you decrease in the pressure by standing on 2 feet instead 1. Okay. So that's the idea about the pressure that you can think. Okay. So example. Okay, so now let's move into the next question. When you visit doctor office, a nurse call out your blood pressure as 130/90. In what units your systolic blood pressure is taken, what will be this value to Pascal, right? So now as we know that this pressure that you are taking in your doctor office is measured in mercury millimeter. So now how you convert into Pascal, you should know the conversion factor, right? So now conversion factor is 1 mercury millimeter is equal 133.3 Pascal, right? That means 130 mercury millimeter is equal to, by considering it as Pascal, this much Pascal, right? So 90 mercury millimeter is equal to Pascal. How you do the conversion? You just times the 133.3 to make into the Pascal. Okay. Okay, so now let's move into the next question. Those all are concept questions, not much problem solving yet, right? And so now let's do this one. A nurse need to inject liquid medicine into your body by exerting 3 newtons, force onto the hydro syringe. And if the barrel of the syringe is 5 millimeters and in diameter, that information is important, and needle is 0.25 millimeters in diameter. So now, how many newtons of force does the medicine come out from the needle into the body, right? So now this question, you see that given is diameter. So that should be given radius in the question, right? Or maybe area is given directly. According to that, you need to process the question correctly. Okay. So now in this question, since given the diameter, we'll need to convert that into radius or find the area according to the uh, hydraulic equation that we have, Pascal principle. I'm just going to draw your syringe first. We'll say I have syringe like this. This end is opening to the needle, right? So now we'll say this is P1 and this is P2, and then you have cross-sectional area A1, cross-sectional area A, right? So now in this case, whatever pressure that you are applying in this place will be the pressure that you are coming out in this place, right? So what that means is pressure at point 1 is equal to pressure at point 2. So now we can write this as force you applied on this side and this side, force 1 and force 2. Force 1 divided by cross-sectional area 1 equal force 2 divided by cross-sectional area. This is the hydraulic lift that we discussed, same formula, right? So now by using this one, you can write the F1. Let's write what is given first. F1 equal 3 newtons given. And then you see that the diameter 1 is given as 5 millimeters, right? So I'm not going to convert in here because you will see it will cancel out in the bottom. Because of that, I just keep it as that. But I'm going to write next one, diameter 2 is equal 0.25 millimeters, right? So I don't want to convert those things because both are in denominator, left and right. So your unit's going to be cancelled at the end, right? But you need to be careful with, if cross-section is given, you can directly use the cross-section in here. But it seems in this case, cross-section is not given, but I know the cross-section is phi r1 squared, that is the radius, but this will be equal to phi diameter, that I write it as d 1 squared r equal twice of r equal diameter, right? So now because of that, I will be able to write this as pi d1 squared divided by 4, right? So similar to that, I will be able to write a2 also pi d2 squared over 4. Okay. So now I have this all the informations, and we're going to plug that in, and then you will see your units cancel out and those things. Okay. So now let's do that in here. So f1 equal, we need to find f2. Let's write f2 first. F2 equal a2 over a1 times f1, right? So now a2 over a1 is pi d2 squared divide by 4 and divide that by pi d1 squared over 4 and f1. So now you see that a lot of things here will cancel out. This part and this part will cancel out, right? Finally, you're going to stay with d2 squared f1 divided by d1 squared. That's why I did not convert any of the units in here, since units will cancel out. So now d2 will be 0.25 and power 2, and going to divide by d1 5 and power 2, and f1 is 3 Newton. So now you will get the f2, and what you expect from f2 in this case, because you have the f1 3 newtons and you inject medicine from that side, and then you have the same pressure, but my cross-sectional area is now lower. When the cross-sectional is lower, to make it equal, your pores that come in the liquid should be what? Is it greater or less? Okay, so that will be less than what you applied in f1. So 0.0075. Okay, so I hope everybody understand that. And now let's move into the part D. Okay, part D again, to observe your Pascal principle, like if you have a depth or if you have a height, how do you going to calculate the Pascal principle, how you use the Pascal principle to calculate the barometer. Barometer is the device to measure the atmospheric pressure, as we all know. So barometer usually made up from the mercury. We know that if you made up from the mercury, the height of the mercury level will be 76 centimeters. That's we known, and we're going to see how it comes. Now, if you use water, we definitely know this will rise up to around 10 meters. But those are numbers. But where this came from is in this question. So now if your barometer made up from the liquid mercury, what will be the height of the mercury? That will be the first part. Let's do for the mercury first. Okay, mercury, most of you don't know the chemical symbol for that mercury, right? So now pressure by using mercury barometer will be, I'm going to write P naught, rho, G, and H. So now what rho? Rho of the mercury and the height of the mercury, right? So now this will measure the atmospheric pressure. Everybody know what is the atmospheric pressure is, right? Let's write that information in here. P naught is given in the question also, 1.01 times 10 to the power 5 newtons over meter square. That's the atmospheric pressure is. That's what you're going to measure. That should be that value. To make that value, what will be the height? That the question is. Now height equal, you see that P naught divided by rho of mercury and the G, right? So now we're going to plug the values in here. Let's do it on the bottom. P naught is 1.01 times 10 to the 5 and divide by density of the mercury given here, 13,600, and then times D value 9.80. If you put this into your calculator, you will get this as 0.760 meters. That is what we are expected. That is 76 centimeters, right? Or 760 millimeters. So now that will be for the mercury. Now you can do the same calculation for any other liquid, but this question is saying water. All right, so water. So now for the water, you have exactly same equation. It should not change your atmospheric pressure, but now density of the water times G and the your new height. Now this case also height will be equal to P naught divided by for water and G. Okay, so now let's plug that into here. And again 1.01 times 10 to the 5 divided by density of the water is given in the question here, right? And times 9.80. You will see this number is 10.3 meters. So that's the reason that we do not use the water barometers, because it is inconvenient and you should have a longer tubes to make the barometer. Okay, so now let's move into the next question. E. A block of wood with length 2 with 7 and 0.5 height placed in the water. What is the buoyant force? I want you to understand how do you calculate the buoyant force acting on the object. So now as we discuss in the summary, you remember that buoyant force is, we will be able to write by using mass of the displaced fluid. So that information is important, times G. So MF is mass of displaced fluid, not the object. Liquid, I'm going to write liquid in here, right? So now if you collect the liquid that coming out from the your main beaker that has the object, then you're going to measure the mass of that and times the G, that will give you the buoyant force. Now, according to information, there is no mass given. So we will be able to calculate the mass by using density formula. You guys know that, right? Density equal mass over volume. That means I can do the density times the volume to find the mass. So now density is directly given of the fluid in here, right? So that will be 1000. And volume, you know that you have a block wood piece with these informations. That means you need to times those things to find the volume. Since everything is in SI unit, I will just do it. After that, my mass going to be come with kilograms, and that will be, hope it will give you around 700 kilograms, right? And then I will be able to calculate the buoyant force. So buoyant force is equal to 700 kilograms times 9.80. That will give you in newtons. Buoyant force is equal to 6860 meters. Okay, so that will be our question number 1 on your worksheet, right? So now we're going to move into the question number 2. Okay. I'm sorry. Okay, so let's move into the, somehow it will not allow me to, good. Okay, let's move on to question 2. Okay, question 2 also, I'm going to make a space in here. Then I can write there, right? Okay, let's do this one first. If there are 2 points, A and B, A is located. I just want you to calculate the pressure in depth and the height. So there is A and B points, right? You are sitting on somewhere here and there is a pressure that we call it as usually atmospheric pressure. But you need to calculate the point A and B. They are sitting same height, but below you and B is located at the distance above you. This is the point B, this is the point A, this is H, this is also H, right? So now calculate the pressure difference at each of these 2 points to the pressure at your position. Pressure at your position is P naught. So now we know that pressure at position A will be able to write P naught plus density. In this case, you have the uh, density of the air, right? Rho GH, it doesn't matter whatever fluid we have. Fluid means air or the gas, right? And then we need to calculate the difference between these two. PA minus P naught is equal rho G and H, right? So in this case, I'm going to take it as air. So density of air will be equal to 1.27 kilogram over meter cube, right? So I'm going to use that value 1.27 and G is 9.80 and H is given 5.50, and then I can calculate the pressure at A with respect to the pressure at your point P naught is equal to 68.5 pascals. Now you can do the same thing for the PB minus P naught, right? So now in this case, PB minus PB pressure, let's write that first as PB. PB pressure is equal to P naught minus rho GH, because your pressure is lower when you go upward direction, right? So now if I calculate the PB minus P naught, since everything is same, only difference is you have negative rho G and H, right? Because of that, PB minus P naught will be same value, but negative 68.5 Pascal. Okay, so now let's move into the part B in the question. So now in part B, you have a garden hose has the unobstructed opening with the cross-sectional area 2 point. So you have the garden hose, you say there is an opening in this end, right? So cross-sectional area, I'm going to write as A1. And this end is 2.85 10 to the negative 4 meters squared. And so now it fill up with the bucket with volume of this much in 30 seconds, right? So now I need to understand what is given in here. So this information is given as the, remember that the flow rate that we discussed, flow rate, we call it, we use the letter Q for that. Q is equal cross-sectional area times velocity, right? So that means if I want to write velocity, that will be Q over A. But this given information, this volume in 30 seconds will give you the flow rate, that is the Q. Q equal 8.00 times 10 to the negative 3 divided by 30 seconds. That will be given in meter cube over second, right? And so now what I need in the question, first, find the speed of the water, find the speed of the water that leaves the hose. First one is we are working with unobstructed opening. So now I need to calculate the V. So we already have the information for the part 1, right? So now V will be Q over A. So it's very simple. You have all the information. Let's rewrite those. 10 to the negative 3 divided by 30 is your Q, and also divide by the area, that will be 2.85 times 10 to the negative 4. And what you are expecting is units of meters per second. You see that meter cube over second divided by meter squared will left with meters per second. So that means velocity will be equal to 0.936 meters per second. Okay, so that will be the velocity if it is on the 1. I'm going to write V1 because of that our first question. Okay, so now second question, what is the difference between first question and the second question? So now you see in the second question, I have the obstructed, right? That means your tube, you see what it says, opening half as much as area. So your opening tube, you're going to make it half cross-sectional area now. Now this is the opening. Let's say it is the A2 and cross-sectional area A2 is given. And now velocity in this point is not same as the velocity of that point. But important thing is this Q value is still the same because you have the same flow rate, right? Right, A2 will be, say, half. You can write half of A1. I don't even want to write the number. I know it is half of A1 is given. And Q will be still the same, right? We have 800, 10 to the negative 3 divided by 30. Now what the question is asking, find the velocity, right? So now flow rate is the constant, right? What that means is, let's write Q equal AV constant. That's what the flow rate means. So when it is constant, what I can say is A1, that is unobstructed in first one, and V1 should be equal to A2 and V2. This side is my A1 side. Okay. So now you can see that I need to calculate V2 will be A1 over A2 times V1. So we have A1 over A2. You can see from here very clearly. Just write that first. Here you can see A1 divided by A2 is the one that I need, right? This will be equal to 2, right? So now V2 will be twice of V1. V2 will be, plug that into 2 times 0.936. That will give me around 1.87 meters per second. And check that your conclusion is correct, because in your flow rate conformation is A and V is constant. When you have narrower tube, velocity is greater. Do you see that? It is narrower tube here. That means I should have greater velocity. So I proved that also in this question. Okay. Okay, so now let's move into this one. Okay, part C. The water tank is open the atmosphere at the top and the bottom opening in. What it says is here also P0, here also P0. That both open to atmosphere, right? And find the speed of the liquid leaving the pipe at the bottom of height h centimeters, and what principle you use here. So now this kind of question, its flow is going and you have different tubes and you have different pressure on those points. So because of that, this will be your Bernoulli principle, right? So that is, you can see sorry for that. So we have Bernoulli principle. right? That's the principle that we're going to use in here, right? So now before that, I need to mark, because Bernoulli principle say in that if you take the pressure plus rho V squared plus rho GH equal constant. That's what it says, right? What that means is if I choose any 2 points in this process, I can write pressure at 1 point plus half density. The liquid is the same in here. Density will be 1 and 2 will be the same. Because of that, I will just write the density in there. And density rho H1 should be equal to second place plus half. So velocity 2 squared plus rho G and H2. Now let's see where we're going to take it as H1 and P1. So I'm going to take this place, and this is the other place that I am working with, right? So this place will say pressure P1, and this place will say pressure 2. So what we know is pressure P1 and P2 both are open to the atmospheric pressure. Because of that, that will be P naught, right? In addition to that, let's write here, I have H2 equals 0, this place, and this place I have H1 equal H, that 25 centimeters, right? And now I think it's ready, and velocity of this point, say V2, velocity of this one, say V1. So now as soon as you can see your V1 that is staying at rest always, because of that, this velocity will be equal to 0. This is what we need to find it out. So now let's put this everything into together. So now both are P naught. Let's rewrite it. P naught plus half rho V1 equals 0. I'm going to just get rid of the zeros. I don't want to put that into here. Keep it here. And I'm going to make this one, we know it's already 0. Okay. Then I have plus rho G, and H1 is now just H, and H is given in the question, right? Should be equal to P2 is also P naught plus half rho V2 squared plus next term, since H2 equals 0, this term will be 0, right? So now we see that P naught and P naught will cancel out. Because of that, V2 I will be able to write, rho also cancel out, and I will be able to write 2GH. If you need more step, please do so. So we have V2 equal root 2G and H. So now we can plug the values. 2 times 9.80 times H is 25 centimeters, and then take the root, and that will give you the velocity that will come on the other end, 2.2 meters per second. Okay, so now we can move into the last. Now we have 2 more parts actually. Let's do this part first. Okay, this is just conceptual understanding of the flow rate and the Bernoulli principle. So let's summarize what we know. Flow rate is equal to cross-sectional area times velocity. What that means, when you have narrower tube, you have greater velocity, right? That is one thing. And other thing is Bernoulli principle saying is if velocity is greater, pressure going to be lower, right? And also Bernoulli principle saying that when H, I mean the depth is greater, pressure going to be greater also, right? Not the height, I'm talking about the depth, right? So now by keeping those in mind, let's label, let's understand this question. I have tube and I have cross-sectional areas labeled. This is my point A, this cross-section is B, and this cross-section is C. So now as soon as you see this diagram, you know that cross-sectional area of A is smaller than cross-sectional area of B, and these two are equal to each other. B and C are equal in cross-sectional area, right? So now you see that when you have different heights, but the cross-sectional areas of the pipes are the same at these two locations. Rank the velocities. That is my first question. When I say rank, make sure that you use the greater, smaller, equal signs, right? So now first one is ranking of velocities. So now after you know the relation of cross-sectional area, you will be able to write the velocity connection, because you know that when cross-section greater, velocity will be lower, right? So now in here, you will see the velocity is greatest at A position. A position is greatest, and then velocity B, velocity, and C, right? That is the ranking of the velocities. Now, rank the pressure of three locations. That will be the next one. A, B, pressure. Now, what we know, when the velocity is greater, pressure will be lower. Then, since A and B is in the same horizontal line, I know that pressure at A is smaller than pressure at B from the Bernoulli principle. But now B and C, you see that B is lower than C, because we know that Pascal principle saying that when you're going downward direction, pressure is greater. Because of that, pressure of B point is greater than pressure at C point. Okay, so now pressure is greatest is A, and then maybe C, and then maybe D. So let's write down that correctly. PA, then pressure at C, and pressure greatest is at D. Okay, so now let's move into our last question in here. Okay, so now in last question, there is a container has a vertical tube connected to the side. This is similar to the mammometer that you are using to measure the pressure at the body pressure. These kind of things made up from this kind of feature. So you can modify this question into different tubes and add in more tubes, or add in your blood pressure, or these kind of situations. Almost everything are the same way by using Pascal principle. Okay, so now connect to its side shown in the figure. Shown in the liquid, reach the level A container and B in the tube. Level A is being 5 centimeters, so it's all informations are on the picture too. But it says you have calculate density of unknown liquid. So you see that your unknown liquid is on the level A in the container, right? So this is the unknown liquid. I'm going to say density unknown. Okay, so this material density is given, and it is oil, right? Oil, right? That density is given. Okay, so now according to these informations, so what we need to do is choose two positions that you know that same vertical, same horizontal positions, we have the same pressure. I'm going to write P1 here and P2 here. What I know is P1 equal P2 in Pascal principle, right? But important thing is this one is open to atmosphere here. This also open to atmosphere. That will be atmospheric pressure at this point and also this point. So now according to that, I know I can write P1 as P0 plus. So this distance, I'm going to label it as H, right? It's H1. And this distance, I'm going to label as H2. Those numbers are given in the question, but I'm going to write the formula by using the symbols first. H1, and then density of unknown liquid times G, rho GH. Yeah, write H first, that's okay. And then P2 also equal to pressure at the top plus. Now it is H2, and now density of the oil times G, right? So now these two will cancel out. After you cancel that out, you will be able to write this formula, and then you will see your G will cancel out. G will cancel out. What you need to find in the question? Unknown pressure, unknown density. So unknown density is equal, you can see H2 over H1 times the rho naught. Okay, so now you see that H2 equal 20 centimeters. I don't want to convert it because those are, can say if you want, you can convert it, but since it is a ratio, you don't want the units in there. If they are both units are the same, you can just keep it as it is. So H1, you can see it is 5 centimeters, right? So now you go here and plug the values, then you will be able to calculate unknown equal H2 is 20.0 divided by 5.0, and density of the oil is given in the question 900. Okay. So now you will be able to calculate the unknown density in kilograms per meter cube. Unknown density is equal 3600 kilograms over meter cube. This is the same principle for all the pressure meters that you have to use. Okay, so that's it for this worksheet.